Whoops, there you go. Bring out the pen. Okay, today we'll discuss lecture 10, set associativity. Um, it's a second part, or at least it's a technique that's good to know because from last week there are limitations to the basic direct map uh, version of caching. So the goal for today is learn about the set associativity. Fully associative, it's the same actually, but we'll discuss it later. And then how do we actually build caches? Right. Now, quick recap. Last time, suppose we have a cache with 8 blocks total, and then each block is also, sorry, there are also 8 blocks each, right? So that means that for one set, you have 1 block of data, right? So it's like there are total of 8 blocks and there are 8 sets of blocks. Okay. Sometimes they sort of interchange, or not misinterchange, but they interchange sets and blocks together. But later on, you'll see that what we mean by a single block and a set. But usually, what happens is that the set bits uh, control which block are you trying to access, right? Now, last time as well, we introduced the concept of set bits to select which block or which set to get the data from. And then we also have tag bits and the valid bit. The tag bits is the upper set of addresses. Let's say, for example, you have a 32-bit address, right? Not the upper set of the addresses, but the upper bits of the address. The first two will always be the byte offset. That's 2 bits long. And then the next three, whatever's in here, will be the set bits, right? That's the one that dictates which block will you have to go into. And then uh, the tag bits are the remaining upper bits, right? And the reason why we have to save the tag bits is to indicate that, hey, this is the actual address that we're trying to save. Because essentially, the entire address and the data that you're using are saved onto the cache. It just so happens that you use the set bits to compress all of those data, right, into a smaller memory, which is the cache, obviously, right? And then, anyway, the important part of the tag bits is that it's used, this is the thing that we use to compare if we actually have a hit or a miss. Because we remember from last time, we can actually put there are several addresses, memory addresses that actually fall into specific set bits. Okay. So essentially, all these things here is first the valid, the tag, the set bits. They are like the addressing in the caches. They're like the memory, quote unquote, memory address in the cache. And of course, you have to save the data all the time. Now, we also briefly calculated the number of bits that you needed to have for the entire system. So, say for example, you have 8 bits, 8 words in total for the total capacity, meaning we have 8 sets of there are 8 words of data that we can store in the cache, right? So that's a total of 32 times 8 bits, right? Which is something. And then you have to calculate how many bits are needed for the addressing. So you have 8 valid bits, then you have 8 times whatever is remaining here. So if there are 2 set byte offsets, 3 set bits, then you have a total of 27 tag bits, right? So you have 8 times the 27 tag bits. I'll put it a T, and then you have 8 times 3 set bits, right? So then you're gonna have to add the 8 words over here. So that all in all constitutes the total number of bits that you're gonna use for the cache. So it's pretty straightforward because the only technique that you have to do is just to, hey, you have to draw the cache, what it looks like, and then you just do some counting. That's it. Okay. So there was a problem from last time. Okay. The direct mapping is the basic cache, right? Where ideally what happens is that all those tag bits, or sorry, set bits, okay, all memory addresses that have the same set bits fall into the same location, right? Like this FFFFC. What else? That's this FFFFDC. All those that end with C actually fall into the same 1111 set bits, right? Now there's a problem here. Um, okay, the problem here is that what if we save FC in the first cycle and then DC in the next memory access? So the tendency is that you'll be replacing that memory location every now and then. Okay. So here's a better example, right? Suppose you would like to access the memory address 04 and 24. So it's this one over here and this one down here, right? If you look at the set bits, they are both 0001. Not a problem, okay? But then, if let's say we put 004 first, so in first cycle, we have 04 here, and then suddenly in the next cycle, you need to access the same location. So you're gonna have to write 24 on it. But then that would be a miss. Why? Because the tag bits of 04 is different from the tag bits of 24. Right? If you look at here, the tag bits of 24 is 0001. Then the tag bits of 04 is 0000. So if the tag bits are different, it's always going to be a miss. So if what happens here is that if we alternate 04 and 24 at the same time, or rather in every memory access, let's say for some magical reason that's what's written in your code, your problem is that you'll always miss. And then you'll have to waste extra cycles on accessing the main memory. So no temporal or time locality occurs because you always have to replace it. Okay. Now the question is, can we actually have a different way for accessing these bits, right? Or using this cache? So let's say, what if we had the capability where we can actually divide the one set or this entire original 8-word set into two different ways, okay? And we call it a two-way because the idea is that, okay, I can use way one or way two anytime I want them to be. Okay. So we'll demonstrate it through an example. Now this is nice because if you observe over here, way one has the same set bits of way two. Okay. And take note, we had to divide it if we're limited with uh, a cache with only 8 words, then we have to split them into two. And if we split them into two, the number of set bits that you will use is also divided by two. So you only are not divided by two, but you lose an extra bit. Okay. Because what you're gonna do is essentially you're gonna cut this into two, right? Such that this MSBs will disappear. Right? I'm gonna cancel that. And then this upper one goes up here, or this lower other one goes down here, or vice versa. Any doesn't really matter. But the idea is that instead of having just one cache, well, it's still one cache, right? But instead of having one cache that are the only bits that you can control, you have two caches wherein you can actually access the same set bits, right? This way, okay, as you see later on, we can write in any way we want to put the data. So let's say in the example of the 04 and 24 again, we can put 04 here or in way 2, does it matter? Then since if 04, let's say, is placed over here, right? And if we put it into, if we try to access 24, we don't have to replace 04. We will write 24 in way 2 instead. I'll show you it in a bit again. Okay. But the important concept here is that we have this thing called an n-way set associative, or some people just call it an n-associativity. Two-way associativity or two associativity or associativity of two, depending how you want to call it. But the idea is that you're gonna have to cut your entire original cache, that's just one way, into two different ways, such that I have two sets, or not two ways, two sets, but rather two ways of duplicated sets. Okay. So I'm gonna show it in a bit. So the idea here is that, okay, note instead of having 3 bits for the set bits, you have two set bits instead. So again, what you're gonna do is that in the main memory, the first 2 bits are the byte offsets. It's always gonna be that way. But then you're just gonna grab the next 2 bits instead of the next 3 bits. Now in the next 2 bits, here's the interesting thing. Okay, let's say for example, 24 can now be written into either set way 1 or way 2. And if you look at the set bits, it's also 0, 1. Not a problem. Now 1, 4 is also the same. It's also 0, 1. But the nice thing about it is that you're not restricted to a single way only. You have 2 ways to write that 1, 4, 2, 4, 0, 4, anything with the set bits of 0, 1. All right. So the idea is very simple. Okay. You just have 2 ways. And I can put it anywhere where I want it to be, right? It's up to you, the designer, how to decide where you want to put it. Okay? You can have your own control scheme, but for now, let's say we will prioritize putting it on the lower way, like the first way. And then if we have to put something again on the same set bit, we put it in the second way. Okay. And this way we can catch all the cases, or as much as possible, we have less number of misses. Right. So I'm gonna go back here again just to make sure. So here in the scenario where we only have one direct map caching, this is essentially a one way because you only have one way to place the data on a given set of set bits. Right. And again, as mentioned earlier, if we put in 0, 4 first and then 2, 4, let's say we're gonna repeat that cycle over and over again. Let's say we did it 6 times, right? So in the first cycle, let's not call it a miss because it was, or rather, yeah, it is a miss, not a problem. But then the second cycle, or in the second memory access rather, if we access the same thing, it's also a miss, right? So if I'm gonna do all of these 6 sequences, they're all misses because we always have to replace that single location. Okay? That's what happens in the direct map caching. Now, if we're gonna go back here, and I'm gonna show you a better example, this one, we won't be having several misses. Okay. Instead, what's gonna happen is that we'll be able to access both. Now look at this. Now say we're gonna use the same 0, 4, 2, 4, and then I'm gonna access 0, 4 again. Right. So in cycle one, nothing's written. Okay. In the second cycle of accessing the data, okay, or rather in cycle one, I need to write 0, 4, or I need to access 0, 4. So it's the first cycle upon startup, nothing is written, right? Now in the second cycle, after writing 0, 4, I guess I'll write it here in way 1. So let's prioritize the lower way first. Now in the next cycle, okay, when we get to 3 onwards, that 2, 4, okay, will be written in way 2 instead. So we don't have to replace the one in way 1. Because here in 0, 4, okay, 0, 4 has both of them, okay, all of them have set bits of 0, 1. You can verify that wrong, but on the first time that we're gonna write it, okay, it's a miss because we're gonna have to write it here. And 2, 4, when we're gonna write it, it's still a miss, but then that's okay. But because instead of writing it here in way 1, and because we know that way 2 is empty, then we write it here in way 2. So if we're gonna continue the pattern 0, 4, 2, 4, 0, 4, 2, 4, right? On cycle 3, okay, when I try to access 0, 4, what happens there is that it's not a miss. It's a hit because it exists in way 1. Now, if I'm going to go to 2, 4 in the next cycle after cycle 3 on the cycle 4, it will also be a hit because it's in way 2. Okay? So anything succeeding here, 0, 4, 2, 4, 0, 4, 2, 4, all these 4 over here, they're all hits. Okay? So I get 4 out of 6 hits as opposed to the 100% miss rate in the direct cache mapping. And it's so cool because it's so we were able to quote unquote temporarily uh, place the data that we need into the different ways is inside the cache. Okay, so it's good because we're not missing. I mean, that's the point, right? We don't want to miss. Now, how do you check if it's a hit or a miss? Remember, it's the tag bits that you need to check if it's a hit or a miss. Right. So when you try to access 0, 4 at first, okay, it's gonna point. Okay, it's going to. I'll show you the drawing later, but it's gonna point into the set bits of 0, 1 first. Okay, and then it's gonna say, okay, can you please look at 0, 1 of all the ways, and then you are going to simultaneously compare is the data or the memory address that I'm looking for in way 1 or way 2. Okay, and then how we're gonna do it is just you're gonna look at the tag bits. You're going to decode the tag bits. Right? If it's in the tag bit, okay, then it's a hit, right? And because both addresses 0, 4 and 2, 4 are inside the cache, right? Because they're inside, just the idea or the fact that they're inside the cache, there will always be a hit. Okay, so that's how simple it is. Now you might be wondering, what happens if we put in 1, 4 or some other bits that have 0, 1 in their set bits as well? Okay. So here's the interesting part. So what if on the fourth cycle, right? So in the first 3 cycles, it's the same as last time. So it's let's do something like 0, 4, 2, 4, and I'm going to access 0, 4 again. And then the fourth cycle, I'm going to write 1, 4. Right? So in the first cycle, nothing happened. So you're just going to write 0, 4. It's going to be a miss. All right? You're going to write it here. This is also going to be a miss, 2, 4 in the second cycle. 2, 4 is not existing in second cycle. So you're going to, on the third cycle, you're going to write it here. But in the third cycle, when you're going to access 0, 4, it's going to be a hit. Why? Because it's the 0, 4 mapping is existing in way 1. Now, in the fourth memory access, when we try to write 1, 4, it is neither in way 1 nor way 2. Now, the question is, where do I want to access 1, 4? Obviously, that the next step is to either replace way 1 or way 2. But is there actually a better way to replace it? The quick answer is that you put it on the data that has been least recently used. Okay. So on this cycle, right, in way 2 or way 4, right, which data was least recently used? Okay. Actually, I think I messed this up. Sorry, I should have put the sequence 0, 4, 2, 4, and then 2, 4 again. Okay, not 0, 4, 2, 4, 0, 4. Okay. It's 0, 4, 2, 4, and then I'm accessing 2, 4 again. So if I access 2, 4 again on the third cycle, it will still be a hit, right? Because it's here. But then on the fourth cycle, it will be a miss because 1, 4, the address in 1, 4 does not exist in the cache. So who do we replace? Do we replace way 1 or do we replace way 2? The quick answer is we have to replace way 1. Why? Because way 1 was the least recently used cache component, right? Why? Because the latest one that we used was 2, 4, right? But then if 2, 4 was used recently, then there's a chance that high probability that we will use 2, 4 again. Because sometimes maybe you put it in the code that you want to use 2, 4 again. Okay? So if that's gonna happen, we're gonna think that okay, if that's gonna happen, then why don't we just replace 1, 4? Replace 0, 4 with 1, 4 instead. Okay. And that's the way how we use the least recently used data. So the idea is very simple. Just replace the one that has been least recently used. Okay. So what we do here is that we use a two-way set associativity. Okay. And then the thing is that again 0, 4, 2, 4, 2, 4, right? And then 1, 4. Okay. For a two-way set associative, we used a used bit. Okay. So we have to add another bit. We call it the used bit. And the indicator of used bit is that if it's a 1, it has been least recently used. So that means that's the one that we're not going to replace. We're going to replace the one with the 0 later on. So if the bit is 1, yeah, it's not least recently used rather. It's the most recently used, the one with the bit 1, because it has been used, right? So for example, 0424241 for again. So 04, nothing. So we're gonna put it here. So at this part, when it goes to the second cycle where we just access 04, right? It has been least recently used. Then we're gonna move to 24, right? So it's a miss. It's still a miss, not a problem. But then when we're gonna access 24 and place the memory in there in cycle 3, right? It will be the least recently used. Okay, we're happy with that. And then we're also going to use 24. It will be a hit, not a problem. It's still the most recently used. So we're not gonna change anything. Now the next problem is that okay, if it has been recently used, not the next problem, but when we access 1.4 and it's not in the cache, then it automatically means that we have to replace one of them. But because it was way 1 that was least recently used, okay, it's way 1 that we're going to replace. So we're going to replace it here. Bam. Okay. And whoops, I forgot. You have to change this. It has to be a 1. That used bit has to be a 1. Okay. So take note that because we accessed way 1, okay, as my recently used to accommodate 1.4, we're going to set that bit as to 1. And then for way 2, we're going to set the use bit to 0. Because way 2 now is the least recently used. Okay. So it's just a matter of tagging, hey, if I access this memory, so or for whoever you access the memory, and if it's in the cache, or rather, if it's in the cache or not in the cache, you're going to set the use bit to be a 1 automatically. Okay. So that's the idea over there. It's very simple, right? Yeah, that's pretty much it for NA set associative. Now, the important part for NA set associative is that you can split the entire cache into two ways, and then I can play because I have the same set of set bits, right? And that means sets word. So because I have the same set of set bits, then that means I can place the data in any of these two. Now, the question is, which data should I or how do I actually approach it? Upon startup, always prioritize the lower way first, the quote unquote the lower way. Okay? The lower way, quote unquote lower rather. And then I have to update my used bits to indicate that hey, this location has been recently used or least recently used. And if I have to replace a new set of data, but it hits both caches, or rather it misses both ways, and obviously I have to replace one of those ways, I have to replace the one that has been least recently used. Okay? Those two concepts are most important in NWay set associative. Now, you must be wondering, okay, how am I going to build this in hardware? It's very simple, really. Okay. So the hardware implementation is pretty straightforward. You just have to create a set of register or memory, the one where you can actually allocate the valid and tag bits and the data. All right. That's pretty much it. And take note that if it's a two-way, the set bits, of course, you also have to, well, you don't really allocate set bits, but rather you slice the memory address and then you extract the set bits. Something very similar to what we do with instructions, right? You slice the instructions to identify the destination, the source register addresses, the immediate, and so on and so forth. But here, all you have to do is just to slice the set bits. And take note, if it's two bits only for the same 8-word cache, right? And then those two bits will be the one to select, hey, which selection or which set of bits will I multiplex, all right, to, or rather, which set, okay, which set of both ways, way one and way two, will I be looking into so that I can compare the tag bits. So we're gonna decode it that way. It's not really a multiplexer, but really a decoder to indicate that, hey, this is the data that this is the row that you're going to grab. Okay. And then after grabbing that, as I mentioned earlier, you have the only way to identify if you hit any of the bits or any of the data or any of the memory addresses in that set. Oops, sorry. If you're going to hit any of the data in that set, as you see over here, you're going to make a comparison. So you're going to simultaneously check, okay, if the tag bits of the memory address that you are loading or the one trying to access is equal to any of the tag of both tag bits rather of way 1 or way 0. So any of those. So you're going to compare it simultaneously. Look at that. This one line over here, this line over here. Right. So it's a pretty simple comparison. In Verilog, it's just like what? Tag of memory is equal to what? Tag of the cache, right? Tag underscore C. Something like that. So if they are the same, okay, then you'll generate a hit. Okay. And of course, you have to plug in the valid bit as well, just to indicate that, hey, was this the data during startup or not startup, right? And then if any of those exist, then you have a hit. And of course, that selection of hit bit, okay, you can add into a multiplexer down here. And then that's the one, that multiplexer itself will be the one to access the data, right? You're going to simply decode and access, hey, this is the data that you. So I'm going to redraw this again just to make sure it's clear. This is all in the slide. So say, for example, in the case of 0, 4, and 2, 4 again, right? And then let's suppose that it was loaded already. So the data here is the 0, 4, and then data is the 2, 4, right? And then let's say I'm trying to access 0, 4 again, right? And then I have the bits 0, 1, the tag, the set 0, 1. It's this pointing to the set, not a problem. And then the tag bits that I'm looking for 0, 4, it's 0, 0, some dot, 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 0, 0. And then so I'm gonna dot, 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 0, 0, and then here is 1, 0, right? And then because I'm loading 0, 0 over here in this path, you can see these two, right? So it has 0, 0 here and 0, 0 here. But then this bit, okay, it's also 0, 0 here. This one is 1, 0. So this one will not assert. So this AND gate, this one will be a 0. Then this one will also be a 0. But then here, because the tag that I'm comparing, that I'm trying to access has a tag of 0, 0 at the end. And then in way 1, that 0, 4 data also, or for that address for 04 data, also has a 00, this comparator will be a 1. And then assuming the valid bits were originally 1, sorry, I forgot to put that. And because this is 1 and 1, then you're going to have a 1 over here. And automatically it will indicate that, hey, I have a hit. And that hit will go to the CPU, and the CPU understands, hey, okay, you have a hit. Very nice, fantastic. Right? Or rather, not the CPU, but rather the main memory or the cache controller, rather. And then it has a hit. Okay, no problem. We won't do any memory accesses. Then automatically, because this hit 1 is pointing to that selection in this MOOC over here, right? So if hit 1 is a 1, then it will automatically select this path. And it will load that data 04. Very easy, right? So it's just a matter of just simple comparisons. And it's very easy to replicate, right? Now the NWay is handled by some extra controller. So yeah, the cache controller, and this thing that you're seeing here is for data reads. Okay. Now sometimes the NWay controller has that least recently used controller. So we didn't put the use bits here, but ideally if you have the use bits over there, every time you try to access, that NWay controller is the one that sets those use bits. Okay, okay. Time check. Okay. So the tag bits are okay. What did I put here? So I guess the important part here is that since the tag bits are those that indicate which is a hit or a miss, you have to the point here is that you have to simultaneously check the tag bits at the same time, especially when you access a specific set, right? And if one of them hits, the multiplexer is the one that selects, hey, which one do you grab? Okay. Actually, I'm tempted to use this as a machine exercise, but uh, let's see if we have time. But yeah, let's see. So now you might be wondering, what if we have a four-way set associative, assuming we still have the same 8 words cache, right? So you could imagine that all those 8 words in the cache, you have to divide it into 4 ways. That leaves you with just each way will have 2 sets of data only. Okay, so you're limited to 1 bit of set selection, right? So now the idea is, okay, it's pretty much the same. Nothing changes. It's just that, okay, you have now multiple sets, 4 sets. And then if, let's say, let's go to everything like 04, all combinations, 1 4, 2 4, 3 4, dot, 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 dot. Everything that ends with a 1 in their set bits, okay, they will be placed here in, and they can be placed in any way depending on how you want to make your cache controller. But then they can be placed here, 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 and here all at the same time. Okay. Any of those. So the if I'm going to place 0 4 1 4 2 4 and 3 4 all in the cache, they can exist at the same time in the cache. Okay, so that's not a problem. Now the same rules apply for depending on, let's say, what happens if there's a 4 4 and you don't know where to put it. The same rules apply wherein you have to use least recently used handling. Okay, but the only problem is it's now more complicated because your cache controller needs to have something like a memory tracker, or like a tracker or a monitoring scheme that checks, okay, which was the least recently used address, right? Things like that. Now for yeah, that's pretty much it. So the advantage is that we're not restricted to the set assignment. We can put in any way. Okay. Now the most extreme part is that what happens if, okay, we have an eight-way set associative. This is what they call the fully associative. That means is that I don't have a set bit. There is no set bit. And the reason why we don't have any set bit is because uh, there's nothing to select from. We only have one set, right? I don't need multiple sets to select a set bit. Okay. And what happens here is that I can put it in any way among here, right? I can put the data in any way. And that's pretty much nice as well. Okay. And it's not gonna be a problem. It's pretty much very much flexible. The only cost here is that you have a much larger parallel decoding, right? So if you go back here originally, right, you here in the two-way set associative, you're going to compare 2 sets of data at the same time. In an 8-way set associative, you're going to compare all 8 of them at the same time. So that sort of adds a little bit on the latency, the combinational latency. And just like last time, um, if you add more combinational logic, what happens is that the slower your processor becomes, or rather, the slower or the maximum frequency that you're going to achieve is going to be much slower because you have to accommodate the logic delay of an 8-way set associative. Now, someone already studied this, by the Patterson and Hennessy book. Okay, and the n-way set associative it uses utilizes uh, n-way set are utilized temporal ut, utilizes temporal locality, as we've seen earlier, not a problem. But here's the interesting thing. So this is the miss rate actually. So the number of misses that you have in a one-way is pretty much high. But if you move to two-way and four-way, you have diminishing returns, right? And then of course, it also depends on the size of your cache. Now, if the size of your cache is really small, well, you have very, very high miss rate. But then, n-way set associative becomes very useful, okay? Because uh, you have, as opposed to just having, let's say you have 4 blocks, and then you're limited to a one-way set associative rather than having a 4 blocks with a two-way set associative, right? You have more temporal locality in this way, in the n-way set associative. Okay. And here, what this block tells you really is that you get higher gains when you have a very small cache size and then you use an n-way set associative. So even though you have a cache size of just 4 kilobytes large, and then between one-way to versus two-way set associative, you gain this much amount of savings. But if you have a very large cache already, uh, this implies that, hey, you're still going to gain some savings, but it's not that significant, right? So between having a 8-way or a one-way set associative at this point, let's say 256 kilobytes of cache, might as well probably don't use a 8-way anymore because the performance of the miss rate isn't that large, right? So a one-way will be pretty much sufficient. Bottom line, use n-way set associative if you have a very small cache. Well, not very small, but you have a smaller cache rather. Okay? And then the trade-off really is that you have miss rate and area. And of course, you have this latency. I forgot the latency of the decoding. That's pretty much it. Now, hold on. We're almost done. Woohoo! Uh, okay, you might be wondering. It's okay. In all the examples that we're using, we only used a block with one word only. If an n-way provides temporal locality, that means all the least recently used data are stored in the cache. Not a problem. But what about the spatial locality? What if there comes a time, let's say, for example, you have this cache, right? And then you start it at 00. And then what if, for some reason, the way you coded or someone coded their program is that at 04 and 08, the data also exists here. So why don't we put the entire, all three consecutive, actually, let's put the fourth one, 0C. Why don't we put all 4 consecutive data in the cache immediately? So we just have one memory access, we grab all 4 and then put it in the cache already. Okay, we put it in the cache immediately. As opposed to accessing 04 first, and then suddenly if you need 04 but it's not in the cache, you have to access the memory again. So why not use add spatial locality that if I have to access 04, okay, I'll grab the entire 04 up to 0C and put it in the cache. Right, so 04, 00 up to 0C, I'll put everything in the cache, and that's it. Okay. Now, we can do that by increasing the block size B to improve spatial locality. Right. Now, the idea is that each set would contain more than 1 blocks. What we had previously is that, okay, if this is the set bits, right, and then let's say 000, or an example earlier, we only had one word. Okay. Now what we want to do is that, let's say we have a one-way set, it still is a one-way, but then per set that we do, we actually save 2 consecutive data, and consecutive in the address. All right. And here's the thing. It's pretty much simple, right? The only thing is that, okay, this time we still have the 2-byte offsets, but this time, since we are only limited to, let's say in our example, we have 8 words only, but then for each set, we have 2 sets of data, 2 sets of consecutive data. All right. So we only have, instead of 3 bits for the set bits, we have 2 bits instead. because we're going to select 4 sets only, where each set contains 2 blocks of data. And then we have a single bit just after the byte offset, right, to select, okay, which block am I going to get, right? So this thing here, technically, it's still a 3 set. It's like you could imagine that it's having 8 sets, but no. The more appropriate way to think about is that I only have 4 sets, but then within a set, I can select in any of the blocks. And then we have these block bits that selects, okay, which among these blocks am I going to use? And the interesting part about it is that if you put them consecutively, they share the same tag bits. Okay, I'm going to demonstrate in a bit. So let's, like this one. Say, for example, we want to access 0000. So the set bits, okay, so the byte offset is already 00, and then, or rather, I'm going to write the entire, just the first 2. This is in hex, all right? So 0000. So the first 2 byte offsets is 00. The next 2 are 0. The next one, rather, is the bit. This is the bit offset. It's pointing to a 0. Okay. So I'm going to store my address access 000, okay, onto the 0 block. And my set bit, by the way, is this one, right? So it's 00. So my set bit is 00. My block bit is 0. So I'm going to store it in here. Now, the tag bits, obviously, the upper one are the same. Okay, 000 as well. 00, da, 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 da. Now, what if I'm going to now, or rather, not if I'm going to access, but because, okay, because 04, the address 04 is the next in line, right? If I'm going to write 04 here, I'm going to erase this a bit. Lip, lip. Because 04 is written this way, 10 underscore 0000 dot, 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 dot. So this is 0x0 and this is 0x4, right? So the first 2 bits are still the offset. I don't care. The next bit is the block bit 1. Okay. And then the tag bits are, the set bits rather, is still 0. So this one will point here, still in the set bit 0. The block bit is 1. I'm going to put it here immediately. And then the tag bits are still 0000. So consecutively, address 000 and 004, or address 0x0, 0x0 and 0x4 are placed both in the cache at the same time. When I actually wanted to access 00 only, I also put 0x4 in the cache at the same time. So technically, we advance the data, thinking that maybe the program will use 0x04 later on. So such that, let's say, when we access 0x, sorry, uh, when we access 0x04 later, so if we access 0x0 first, that was a miss. Okay, it was a miss. I'm gonna rewrite it. It's gonna ask 00. The first time we put a 00 first, it was a miss because we needed to load it first, right? But the next time we access 04, right, it's already in the cache. So it's a hit. All right. It's a hit because spatially we were able to put the data in the cache. Now, interestingly, those blocks, oops, where's my mouse? Those blocks have the same set bits. The only time where they're different is because of the block bits. Not a problem because it's contained, that information is contained in the memory address. And then the tag bits for both are the same. So I am sure that if the tag bits, or rather the tag bits of 00 and 04 are always the same, then I am guaranteed that I will get a hit, right? And then it's just a matter of selecting, hey, which block am I going to use? That's pretty much it. Now here's the thing, you don't need to compare these 2 bits simultaneously if it's a hit because the tag bits are the same. And it's unlike the n-way set associative. I'm going to go back here, right? It's not unlike the n-way set associative where I have to compare the tag bits all at the same time. No, okay? I don't have this decoding anymore if I increase the block size. Okay? So it's spatial locality allows us to do that. Okay? That I don't have to, whoops, here's the one. I don't have to compare all the tag bits for this data and this data at the same time. Why? Because they only share one tag bit. So that's not a problem. Okay. So, and the data is easily decoded by these 3 bits, actually. Right. It was just a clever way of trying to divide the original set bits for the one-way or the direct map cache, right? There were 3 set bits, but then if rather than having to, because I don't have spatial or temporal locality in a direct map cache, let's try to overcome these issues with adding extra blocks per set. Okay, so the data is easily decoded by the tag, set, and block bits. I don't need other extra decoding. So that's the advantage of a block. Okay. The only disadvantage is that, let's say, for example, how do you put it? What if I'm going to access, it's not 00 and 04 anymore, but rather 1, 0, and, sorry, 00. What's a good example? Or rather, what happens if we access memory that has the same set bits, right? That's the only time we're going to have an issue. Okay? Because it's possible that they will have the same set bits, okay? But then they don't have, they have different tag bits. Okay? So let's try, for example. So if 0000 is underscore 000, so if I'm going to change the tag bits, this is the bits, this is the tag bits. Yeah. What happens if I access 10 and 0x14? Okay, 0x10, 0x14. So let's say 0x10. If I'm going to go to 0x10, 000, okay, offset these two bit, block bit, not a problem. But then the set bits, oh no, this is going to be placed over here. Set bits would be in here, up here. So that's not going to be a problem. Let's say 20 rather, not 10, but 20 and 24. Okay. So if it's that way, 20 and 24, okay, there. Okay. So if you compare the tag bits of accessing 20 and 24, write that 0x20 and 0x24, right? If I compare the tag bits of 0x20 and 0x24, it's always going to point to the same set bits, 00, but then they have different tag bits, right? For a 000, it's going to be 0000, but for a 24 and 2024, it's going to point to the 10 bits, right? And then if you have a data that alternates between 0x00 and x20, you're going to have to replace this several times. Okay? So that's the only problem where increasing block size is not useful. Okay? So just a heads up. Bottom line, if they have different tag bits but point to the same set bits, that's the problem where block sizes won't be useful anymore. Okay, but don't worry. That's jumping from 00 to 24, 2024 is pretty far. Okay, that's like 16 bits away, or rather, uh, 32 bits away ish, or 32 addresses away. Okay, so what happens here? What happens if we have a block size of 4 instead? Okay, then you need 2 bits for your block bits because you have to select which bit you're going to use. So assuming we still have the size of 8 words, right? And then I only have I have now a block size of 2, okay, or 4 rather. I need 2 bits to select the block, and then it reduces the set bits because I now only have 2 sets to select from. Okay. So it's just so the idea is the more blocks that you put in, the higher the number of block bits, the lower the number of set bits. But the total the total bits that you're gonna use is not gonna change. Okay, it's just a trade-off between the two. Now it's possible that you put 8 blocks and you only have 1 set. The only problem there is that you're storing everything from 00 up to 8, so that's probably 1C. Okay. So from 00 to 1C, you're going to store all those spatially consecutive blocks, but not in blocks that are, or not memory addresses that are far from that spatially consecutive block. Okay. Now here's the interesting part. You can always increase the block size because having spatial locality is just as good as, hey, I'm just adding several nearby memories, right? But the problem is that someone tested that out, and then they figure out, okay, the miss rate that on average that you're gonna get is that there's an optimal point in between. Okay, so ranging from a small cache size to a large cache size, it's somewhere having a block size of 64 seems to be the most optimal. because if you increase the block size even further, there's a higher chance that the miss rate starts to increase, because remember, the block is storing consecutive data. So if you miss the consecutive data, or the data that you need is not in that set of consecutive data, then you're going to have a miss. Okay. So this is just a good FYI that there sort of is an optimal point where you start to see the part where the optimal block size for large memories, or just for caches, like 4 kilobytes to 256 kilobytes, is somewhere around 64. Here, the interpretation of this our lower part here for the 256 kilobytes is that it has diminishing returns. It's like it still goes lower actually, but it starts, it's not optimal low, or not, it's not a good cost anymore. Okay, so that's just a good FYI. Okay, for a very quick example, this is the last time check. Oh my god, this still reached 1 hour. Why? Okay, anyway, suppose you have a cache where it has N2 set associativity, and then it houses two words per block, and then where one word is still 32 bits long. It has a total size of 32 kilobytes, not kilobytes, but kilo words rather. Take note that's 30, approximately 32,000 words. Okay, well, not exactly 32,000. It's like 2 to something that gives you 2 to the 32. And then your address bit size is still 32 bits. Show how you would slice the main address to show the tag set, a block, and byte offset. Okay? Very simple, right? Very simple. So if I have my main address, right? So the first 2 bits in my main address will always be the byte offset, right? It's not gonna change. Okay? And then automatically you should identify, okay, I have each block that I have. So if I'm gonna draw it here, right? It's like I have a two-way such associativity. Put it. So this is way one, way two. And then for each way, I have the set bits, right? The set. And then for each set, I also have the block, right? The block to select which data I'm going to select. Okay. So I have the block bits of the block. And let's say these two selections are as data one, data two, da. They're all data. Now, because I have two blocks, or rather per block, or per set rather, per set, I have one block, right? Sorry, per set, I have two blocks, right? Two blocks. This is uh, block one and then block two. I'll just write that down. So I need, immediately after the byte offset, I need one block bit. Okay, so I'm gonna write, let's say an X. It's just like one block bit. Okay, this one here is the byte offset. Okay, not a problem. Okay. I have one block bit and then I have a byte offset. Now the tricky part here is that, okay, if that's the case, then it's as if my entire block, if this were to be a one-way block or a one-way cache, I have, how many sets do I have? I have 32,000 kiloword sets. So that would be approximately 2 to the 16, if I'm not mistaken. Was it 2 to the 16? Nope, 2 to the 15. So that's around 2 to the 15. I have 2 to the 15 word selections. Okay. If it were to be a one-way, and then each uh, set has two blocks, block one and block two, I would need 2 to the 15. I will need 15 bits for the set addresses to select each block, right? So I need 15 bits for the sets. Okay. But then take note, I have two-way set associativity. If I have two-way set associativity, what happens here is that I have to divide that 2 to the 15 even further. Because, why? Because I only need, because I can write uh, all those 32K bit words, right, are split into two, right? So actually, wait, let me repeat that. I think I messed that up. Uh-huh. So again, if it's a one-way and I have two blocks, right? Or no, let's try to do it step by step. It's very much clear. I'm gonna redraw it. Whoop, boop, boop, boom. Okay, if I had a one-way, if I had a direct map block, I have a selection of 2 to the 15 rather. Okay. I can select 2 to the 15 because 2 to the 15 is approximately, I'll put it here, 2 to the 15 is approximately 32 kilowords, 32 kilo selections. Okay. Now, if I had the direct map cache, then I need 15 bits to select any set in that direct map cache. Okay. But then it said that, okay, if that's the case, okay, I have, where did I put that? I have 2 words per block. So I have to divide all of this. Instead of, it's still a direct map cache, right? But then each set that I'm selecting, each set here, is already pointing to 2 words, right? So that what happens there is that I'm essentially dividing my entire set into 2. So this time I only have 2 to the 14 selections because I'm already putting two words into one set. Okay. So in total, instead of 2 to the 32K, I have 2 to the 14, which is approximately somewhere around 16K bits, 16K kilo selections rather. Okay. So that's what happens if I have 2 words per block. But then I have a two-way set associative. So that means I have to divide this thing into 2 such that I will get something like, okay, I have this my first set. Okay, this is the DM, wherein it has 2 blocks, not a problem. Okay, this is the set. And then I have my second way. So this is way 1 and this is way 2, which is also the same. Right? I still have, that's not a direct map anymore, sorry. This is the block selection, this is the block selection. Okay? But this is a set selection. Because I have to divide it by 2 even further, I need 2 to the 13 this time. So essentially, okay, this is the setup that I want. And because I have 2 ways and 2 blocks each, this is what my cache looks like. I need 13 bits for my set bits. So in here, I need 13 bits for my set bits. Okay? So all in all, okay, so 2 byte set, 2 byte offsets, 1 bit, 2 bit byte offset, 1 bit block selection because I'm just selecting between 1 or 2 blocks, and then 13 bit um, set, right? So how many for the tag bits? So we need the tag bit over here, the tag. So if this is 13 plus 1 plus 2, and then the entire memory address is just 32 bits. If you do the math correctly, this is 13 plus 1 plus 2, 16 bits minus 32. That's a total of around 16 bits as well. Okay? So that's 16 bits tag bits. So this is what it looks like, right? So that was the solution. I just put it in words here. 16-bit tag bits, 13-bit set bits, 1-bit block bits, and 2 bits byte offset. That's what it looks like. Okay? That's how you will slice your main memory address. Now, last but not the least, time check. Oh my gosh. Okay. Suppose the cache includes valid bits and used bits. What is the total size of the cache? Right. What is the total size of the cache? Also, take note. I'm going to rewrite it here. So, it's a two-way set associative, right? So I have my 2 blocks here. It's like the blocks. Now each block contains 2 sets of data, right? Each block contains 2 sets of data. So I have 32 here, 32 here, 32, and 32. I can store that much. And then right after that, I have the set bits, okay, which is around, which I mentioned earlier, it's 13 bits wide. Okay. And then in the set bits, we also have the tag bits. So the tag is, we mentioned it's around 16 bits. Set 16 bits. And then we added of course, each component needs a valid, and then the use bit, the valid, and then the use bit. Right? Well, technically, you just need to look at one set over here. Like this is 1 bit, 32 bits, 32 bits. Just look at this one set. So I have 1 bit valid plus 1 bit use block, or use bit, plus 16 bits for tag, plus 13 bits for set, plus 64 bits for the 2 data words, the 2 words that I'm storing, the data. Okay. That's a total of, how many is that? 1 plus 1 plus 16 plus 13. 1 plus 1 plus 16 plus 13 plus 64. That's a total of 95 bits. Okay. Hold on, is that correct? 32 plus 2 plus 2 plus 32. Aha, that's not. Yeah, so that's a total of 95 bits, right? And then what you're going to do next is that, okay, that 95 bits, how many entries do I need? Right? How many entries do I need? So the selection here is not 32K, and that's not 2 to the 15, but rather the selection of one selection, because I cut the entire bits into two, right? It's going to be 2 to the 13. Right? So 2 to the 13 times 95 bits. So 2 to the 13 times 95 bits becomes 2 to the 13. Oops. 2 to the 13 times, oh, times 95 bits leads you around 700, approximately 778K bits in total. Okay? All right, let me double check. Did I do that right? Yes, that should be the one. Okay? That should be the one. Actually, I have the solution here, but I think this is wrong. This is not, this isn't right. Yeah, I'm gonna erase that. Whoop. This is the one you have to follow, right? So it's just a matter of drawing it out, counting the number of bits, and then counting the number of entries that needs to be loaded. Okay? So what else? Let me see. Group. Yeah. So in summary, we learned about set associative. We have fully associative memories, and we learned how to build caches. So yeah, that's pretty much it for this today's lecture. What? Umabot tayo 11. What? Okay. Yep. I'm gonna end the recording there. Oop, not the stop share, but